In this video, we're going to prove an important result about the structure of groups of prime order. And one reason we do something like this is just because anytime we can know what the structure of a group is just from the number of elements it has, that's interesting. That's always interesting and worth doing in its own right. But the other reason we're doing this here and now is to illustrate the power of the result that we proved, that the subgroup of a finite group has to have an order dividing the order of the group. In other words, if H is a subgroup of G and G is finite, then order of H has to divide order of G. It turns out this is a really powerful result, and we'll see one reason why in this video. All right, so I'm going to start by spoiling the result. Here's the theorem. Every group of prime order is cyclic. We're not going to prove that immediately. We're going to start by proving the following lemma. So the lemma is, if G is a finite group, and A is an element of G, then the order of A divides the order of G. That's an interesting result, right? Anytime you have a group, every element of that group has to have finite order. We proved that in a previous video. But not only does it have to have finite order, it has to have order a divisor of the number of elements of G. Here is the proof. So let's assume G is finite. And A belongs to G. Okay? And just so that we have some handy symbols around, we're going to let N be the order of G. Okay? Now, if A is an element of G, one thing that I know is that I can construct the cyclic subgroup generated by G. So consider the cyclic subgroup generated by A. This is a subgroup of G. We've proven that before. And so, by Lagrange's theorem, the order of this subgroup has to divide the order of G. So, in other words, the order of this subgroup has to divide N. That's what we said the order of G would be. All right, but what does that mean? Another thing that we've proven about these cyclic subgroups is that when the order of A is finite, the order of this cyclic subgroup is the same as the order of A. And that's because this subgroup consists of all powers of A from A to the 0, which is the identity, to A to the 1, A to the 2, all the way up to A to the K minus 1, where K is the order of A. And then once we get to A to the K, we're back to the identity. And so these are all of the elements in this subgroup. And there's a total of K of them, K elements, where K is equal to the order of A. So this just shows, once again, that the order of the cyclic subgroup generated by A is the same as the order of the element A itself. All right, we're going to use that fact now. Since the order of the cyclic subgroup generated by A is the same as the order of A itself, we have the order of A divides N. So that means the order of A divides the order of G. And I believe we're done. That's what we wanted to prove. Yay. Okay, so that's cool. So not only do we know that the order of a subgroup has to divide the order of the group, the order of every element of a finite group has to divide the order of the group. And in fact, this lets us prove something else. This is just an interesting fact. And it's not going to be so important to proving our major theorem here. But I'd be remiss if we didn't prove this. If A belongs to G, a finite group of order N, then A to the N is equal to the identity of G. Now, why is that true? Well, here's why. Suppose G is a group of order N, and A belongs to G. All right, then I know the order of A is a divisor of N. That's the result we just proved. That's the lemma. Okay, so we know the order of A is divisor of n. Just for symbolic convenience, let's say K is the order of A, just so I don't have to wield this order of A symbol around all of the time. Okay, so let's say K is the order of A. Then I know A to the K is equal to the identity. That's what it means to be the order of A, is that A to that power is the identity. And so, since we know K divides N, we have N equals K times Q for some integer Q. Okay, but then, remember, I'm trying to prove something about A to the N, so at some point we should probably just try calculating that and see if we can get there. We know A to the N, well, that's equal to A to the KQ, because we said N was equal to KQ, and then by properties of exponents, that's A to the K all raised to the Q, but then we know A to the K is 1 because K is the order of A. So that's the identity of the Q's power, and that's the identity. So that proves the statement that I've written here. So that's interesting because this means every element of a finite group, whether abelian, non-abelian, nice, not nice, every element of a finite group raised to the power equal to the order of the group is the identity. Very interesting. Okay, so now back to our major theorem. I mean, if you thought that was interesting, wait till you see this. We're going to prove that every group of prime order is cyclic. And once we know it's cyclic, remember this, we know that, oops, let's zoom back in there. So once we know that having an order equal to a prime, let's call that prime P. So if the order of G is P, a prime, then it's cyclic. And if it's cyclic and has order P, then G is isomorphic to Z mod P. And I think, by the way, that's Z mod P under addition, not multiplication. And I think Galilean uses this symbol instead for isomorphic. I don't care which one you use. I think we'll probably not be confused if we use both of those symbols because we're not going to use them for anything else. All right, so anyway, let's prove the major theorem now. Proof of theorem. All right. Very exciting. All right, so let's suppose G is a group and order of G is equal to P, P a prime. All right, then here's what I'm going to do. I'm trying to prove that G is cyclic, so I'm going to try and find something that would generate all of G, an element that would generate all of G. But I don't know how to do this because I don't know what my group is or what it contains. I know it has an identity element, and that identity element is in no way going to generate all of G. All it generates is the identity. So I need to pick something else. So that's exactly what I'm going to do. Absent any other information about how to pick this element, I am just literally going to pick something else. So let's pick A to be a non-identity element of G. And I'm just going to ask the simple question. And by the way, once I ask this question, you might want to pause the video and see if you can figure out how to complete the proof, because I think you might be able to. So the question is, what is, just put a little question symbol there, what is the order of A? Seriously, take a minute and think about that. See if you can figure out what's going to happen next. I'm going to go ahead. So because the order of A must divide P, that's the order of our group, that order has to equal 1 or has to equal P. If the order were 1, then let's make sure that's clear. That's the order of A. If the order were 1, then A would have to be the identity because we'd be saying that A to the first power is the identity. That means A is equal to the identity. And that contradicts our selection of A as a non-identity element. So that means that the order of A has to be P. But wait, what does that mean? Using the fact that we used earlier, that the cyclic subgroup generated by A has the same order as A itself, the order of that subgroup is P. Okay, but wait. This subgroup is a subgroup of G, and this has P elements. Okay, being a subgroup means, among other things, that you are a subset. So if this has P elements, if G has P elements and this subgroup has P elements, well, then what does that mean? They have to be exactly the same elements. So this has to have, I'm going to need a little bit more room here, all the elements of G. Okay, so that means the cyclic subgroup generated by A, that's all the elements of G. In other words, A generates G. So G is cyclic. And what's outrageous about this is that I wasn't even that careful. I mean, I just picked any non-identity element of G and got a generator. So another thing that this proves is that in a group of prime order, any element that is not the identity generates the whole group. That is super interesting. And one more little thing I'll mention without having to write anything else is I think we proved at one point that every cyclic group is abelian. So now we know not only is every group of prime order cyclic, but every group of prime order is abelian. So keep that one in your back pocket.